Hey guys, welcome back to another chemistry lesson. This lesson is on how we classify matter in general chemistry. So first, we need to talk about the definition of chemistry. Chemistry is the science that seeks to understand the behavior of matter by studying the behavior of atoms and molecules. So it's by looking at these atoms and molecules that we can sort of classify them, and that's what this is going to be talking about. So first, why do we care about atoms and molecules? So the behavior of atoms and molecules is what determines the behavior of matter as a whole. So it's really important that we understand those things so that we can understand why matter does what it does. So atoms are the submicroscopic particles that constitute the fundamental building blocks of ordinary matter. Blah, blah, blah. That's book definition. What it really means is they're the smallest parts of matter that still have the characteristics of whatever that matter is. So it's the smallest piece of, let's say, carbon, the smallest chunk of carbon that I can have that still acts like carbon. There are things that are smaller than atoms, but when we get smaller than that, we're now talking about electrons and protons and neutrons, and those behave the same no matter where we get them. So atoms are the smallest piece of an element that still behaves like that element. And then when we put those things together, we get molecules where multiple atoms are chemically bonded together. Free atoms are very rare in nature. We hardly ever see them. So what we are normally seeing are atoms that are bonded together. So small differences in atoms and molecules can result in really big differences in the substances that they compose. So for example, I mentioned carbon a minute ago. There are several ways that carbon can bond to other carbon atoms, and the two big ways that you would be familiar with are graphite, which is what is in pencil leads, and diamonds, which we know what diamonds are. The sheet structure is why pencils work like they do, right? So we can see here in this graphite that we have a sheet, and it is not bonded to, but it is interacting with the sheet right here below it. And then it is interacting with the sheet right here below it. So these differences between this very two-dimensional structure here and this three-dimensional structure here are what makes the diamond see-through and one of the hardest substances that we know. But graphite is what goes in our pencils, and the lead makes marks on paper. And the reason for this is, as we drag a pencil lead across the paper, what is happening is this layer will come off, and then the layer underneath it will come off, and then the layer underneath it come off, leaving a trail of layers of graphite on the paper. So that really different three-dimensional structure leads to really different properties. Right, so we need to talk about matter before we can talk about classifying it. Matter is anything that occupies space and has mass. And so we can either talk about this matter according to its state or its physical form, or its composition, which is the basic components that make it up. And if we talk about state, we can classify matter as solid, liquid, or gas based on the properties that it exhibits. So let's talk about that first, states of matter. So let me start by saying that most of what is on the next few slides is either common sense or information that you have been learning for the last 10 or 15 years of school that you've done, right? But what we need to do is review this so that we can then talk about it more deeply. So atoms or molecules have different arrangements in solids, liquids, and gases, which is why solids, liquids, and gases act differently. The spacing between the particles, the freedom of movement of the particles, all of this contributes to why they behave differently. So in solids, our atoms or molecules are packed really closely together in fixed locations. So the particles can vibrate, but they can't move around one another, which is really important. So as a result, our solids have a fixed volume and rigid shape. Those are terms that you should know. right? Solids can be crystals, like the diamond that we previously spoke about. And what makes them crystalline is the atoms or molecules are arranged in a long-range repeating order. It is a three-dimensional structure that we know what it is, right? So examples of this would be table salts, diamonds, whatever crystals, Susie uses to, I don't know, put good vibes in the universe. I'm not a crystal person, I don't know. But those crystals have that long-range three-dimensional structure. So we call those crystalline solids. But not all solids have a three-dimensional structure like that. So we call those solids amorphous. A meaning without, and morph meaning shape. So amorphous means without shape or without that long-range order to their particles. So things like glass and plastic are going to be our amorphous solids. Liquids are also closely packed together. The difference here is that they are free to move around one another. So there is more kinetic energy in our liquids than there is in our solids. That is why they are at a higher temperature. And that also means that any interactions in between the individual molecules or atoms have been sort of stretched to give that freedom of movement, right? Liquids have a fixed volume, but not a fixed shape. So 100 milliliters is 100 milliliters, whether it's in the shape of a cup or in the shape of flat because you spilled it on the floor, right? So same volume, not the same shape. So the liquid's ability to flow is what allows it to assume the shape of its container. That's why when I spill my drink on the floor, it doesn't maintain that cylindrical shape like it was in my cup. It now becomes flat, right? So we all know what liquids are: water, alcohol, gasoline, etc. Now, gases are types of matter that have a ton of space in between the particles. They are more empty space than they are particles, which is why we can see through them. This is why air is see-through, because we can't see the particles because they're so far apart. They are free, the particles are free to move around each other, and they do so at very high speeds with a lot of energy. So because gases have a ton of empty space, gases are compressible, which is why you can take, say, an hour worth of air and pump it into a scuba tank that's only 22 liters. So gas is compressible, and that's a big part of what makes gases gases. So we have talked about classifying matter based on its phase. Now we're going to talk about classifying matter based on its composition. When we classify matter based on its composition, we do this in two ways, based on whether it's all the same stuff or all different stuff, how it looks, etc. So let's talk about that. So first and foremost, we can talk about pure substances or mixtures. So pure substances are if it's all the same stuff, one component with a consistent composition throughout the entire thing. A mixture is made up of two or more components, and we can vary from place to place. So we're going to start with our pure substances. We've got two kinds of pure substances. We have elements, so all one type of atom, or we have compounds, where we have atoms bonded to each other, and then it's all the same of that. So an example of that would be like water molecules. Water molecules contain hydrogen and oxygen in a specific ratio, 2 hydrogens, 1 oxygen. But when we have a pure substance that is pure water, it is all H2Os, right? So the easiest way to determine which category the substance falls in is to whether it can be found on the periodic table as written. If it is an element, that exact word or that exact symbol will appear on the periodic table, right? So if it's carbon, carbon is on the periodic table. Carbon tetrafluoride don't even know if we really do that. But anyway, carbon tetrafluoride, which is CF4, does not appear as CF4 on the periodic table. So that would be a compound. Right? Our elements are substances that cannot be chemically broken into simpler substances. They are the building blocks of matter, and they are composed of a single kind of atom. A compound is composed of two or more elements in fixed, definite proportions. So I mentioned that previously. Water is H2O. There is always two hydrogens and one oxygen. If it's not two hydrogens, one oxygen, then it's not water. All right, now we go to the other kind, where we have mixtures, right? So instead of pure substances, element or compound, we now have mixtures that can be either heterogeneous or homogeneous. Now, hopefully you have the background knowledge for this, but if not, I'm going to teach it to you now. The prefix hetero means different, and the prefix homo means same. And we have seen hetero and homo in other areas of our vocabulary that are completely not science related. It means the same thing, right? So heterosexual, you like someone of a different sex. See, still different, right? Homosexual, same sex. Homo, same, right? So the prefix here literally tells you what to look for. The easiest way to figure out what category the mixture falls into is whether or not you can see that it's made up of different stuff. It's that simple. Now, heterogeneous mixtures, as the name indicates, hetero meaning different, is a mixture in which the composition varies from one region of the mixture to another, and it is made of multiple substances whose presences can be seen. So an example of this would be a sand and water mixture. If I have a cup that has sand and water in it, I can see the two different parts of that mixture. I can see the sand and I can see the water. Another example would be like a pepperoni pizza. I can see the pepperoni, I can see the cheese, I can see the crust, I can see the sauce, right? It's literally, visibly, can I tell that there are multiple different things in there by what I'm looking at. Homogeneous mixtures, remember homo meaning same, is made up of multiple substances, but it appears to all be the same. All portions of a sample that have the same composition and properties as the sample, so like sweet tea, right? We know that if you've ever made sweet tea, we know that there's the stuff that makes it tea, the stuff that makes it liquid, so water, if you've ever made it, and then the stuff that makes it sweet, sugar. We know all that's in there. But when I'm looking at a cup of sweet tea, I can't see those things. I see brown liquid, right? So because it all looks the same, we call it homogeneous because it is the same composition all the way throughout. Uniform composition. And this is because the atoms or molecules that compose them mix uniformly. Whereas if you think back to the sand and water mixture, those things do not mix uniformly. If I have a cup of sand and water and I scoop off the top, I'm going to get probably 100% water. But if I go scoop from the bottom of the cup, I'm going to get mostly sand, but it's wet sand, so we know there's water there, right? That is not the case with a homogeneous mixture. Wherever I scoop from is going to be the same, no matter where it is. So when we have mixtures of things, this is how most chemical reactions end up happening, even on an industrial scale. What we end up with is mixtures. And we have to be able to separate mixtures because, generally speaking, if we're talking about industrial chemistry, we're trying to make one thing. And we don't make one thing, so we need to separate out that one thing. So the different components of the mixtures are going to have different properties. So we can use that to our advantage. So there are several ways that we can separate mixtures. First is decanting. So our mixture of sand and water can be separated by just pouring the water off the top. Now, depending on what the solid is, you may have to do that more carefully or not. With sand and water, it's pretty easy to pour off just the water. But you just literally take the cup, pour the water off the top, and then leave the sand in the other cup, right? Now, if we have an insoluble solid and a liquid that's not easily separated, like through decantation, then we can use a filter where we have a filter paper in a funnel, and it's going to catch the solid, and whatever the liquid is in will pour through. And this is really helpful if you've got stuff that sort of suspends in the liquid rather than settling to the bottom like sand does. Sand particles are really big, they settle really quickly, but that's not what happens all the time in chemical reactions in the lab. And then we have distillation. Now, distillation is how we make spirits. We do a lot of other things, but spirits, as in drinkable alcohol, this is the most familiar scenario for you for how we use distillation. So when we have homogeneous mixtures of liquids that have different boiling points, what we can do is boil one and not the other. So when we make our, say, whiskey, we have ethanol and water in our mixture. Ethanol boils at about 85 degrees Celsius and water boils at 100. So if we can heat up our mixture between 85 degrees and 100, what'll happen is the ethanol will evaporate, the water will stay, and then we can collect that gaseous ethanol, condense it in our condenser, and get liquid out on the other side. So if you've ever taken a tour of a distillery, this is what you're going to see happening there. So the more volatile liquid, the one that will evaporate more quickly, is what gets recondensed and collected. So this is how we would separate those two things. Okay, now that we've talked about matter, let's talk about properties and changes in matter. So there are two different types of properties. There are physical properties and chemical properties. Physical properties are properties that a substance displays without changing its composition. So odor, taste, appearance, color, melting point, boiling point, all of these are physical properties. Chemical properties, on the other hand, only appear when you are actually changing the composition through a chemical reaction. So corrosiveness, acidity, toxicity, those things are chemical properties. So the way to figure this out is to just ask yourself, is the substance the same chemical before and after you observe the property? Right? I can observe that a rotten egg stinks. It is still a rotten egg before and after. So odor is a physical property because it is the same before and after. If it is different afterwards, then it's going to be a chemical property. So I can't observe how flammable a piece of paper is without lighting it on fire. Well, after I light it on fire, it's not paper anymore, it's ash. So then that would be a chemical property. The flip side of that is a change. So physical changes change just the state or appearance of a substance. We're not changing the composition, just what it looks like. The atoms or molecules do not change their identity during a physical change, but they do during a chemical change. We are changing the composition of the matter. So what we're doing is rearranging and transforming all of the atoms, changing what's bonded to what in order for a chemical change to occur. Right? So here we've got iron atoms. After iron rusts, we get iron oxide, right? We no longer have iron bonded to iron. We have iron bonded to oxygen. This was a chemical change. Here, I have liquid water. I am boiling it, and I'm getting water vapor or gaseous water. It was water before, it is water after. So this is a physical change. So again, the easiest way to figure this out is to ask yourself, is the substance the same chemical before and after the change? If it is the same substance but just looks different, then that was a physical change. If it is a different substance altogether, then that is a chemical change.